cloud.
Yeah.
All right. And then I'm gonna just do this so we don't have this on the screen. Should be good. Okay. Wow, it's a lot of people. Should I just introduce myself, or
I can so I think, well, we all know Yacine, but in case anyone doesn't, he got his PhD from Caltech in 2011, working under Chris Harada, who was my neighbor actually for a while when I was a postdoc. So that dates me, but in any case, and then you did 2 postdocs, right, at IAS and Johns Hopkins with Kamienkowski at Hopkins, and then came here in 2017, right? 7 years ago. Yeah. And so Yacine is interested broadly in the early universe. I guess most recently, a lot of your work has been on primordial black holes, which are, a really fascinating thing. So that's the idea that some mechanism in the early universe produced a population of black holes that are still around. And those could be relevant for dark matter. They could be relevant for LIGO, the events that LIGO is detecting. And he's worked on many other topics in the early universe. You received the Helen Warner Prize and the CIFAR, how do you pronounce it, Azrieli? He's a CIFAR Azrieli Global Scholar. So yeah, and please take it away, Yacine.
Thank you.
Thank you.
All right. Thank you for coming despite the change of schedule. So let's get started right away. So my goal is to Andre understands more than okay, and that I can change slides, but I cannot. Okay, it works. All right, so let's get right to a brief executive introduction to dark matter for those who may not have thought about this. So across a very broad range of astronomical systems, ranging from the smallest of galaxies through large galaxies, through clusters of galaxies, and all the way to large cosmological scales, we can estimate the masses of the systems in 2 different ways. First, you can count stars, you can count galaxies, you can estimate the total gas mass, and that gives you some visible mass. Second, you can use the dynamics of the systems, how fast the galaxies rotate, how fast galaxies spin around in clusters, how fast structures grow on cosmological timescales. And combining these dynamics with Newton and Einstein's laws of gravitation, you can infer a total dynamical mass, okay? And what is observed across the explosion of scales is that these 2 masses are very different, and the dynamical mass is systematically and significantly larger than the visible mass. So there's 2 ways to interpret this. Either Newton and Einstein were wrong, or, and this is what we're going to take in the start, this approach, there is simply some invisible matter, which we're going to call dark matter. So under this assumption, there is some dark matter running around, and in fact, we know very precisely how much of it there is, and we know this very precisely from measurements of the cosmic microwave background, which I will explain in a little bit more detail later on. But so it is 5.36 times the amount of regular matter within a % precision. Okay? What we do not know, of course, and this is the big question, is what dark matter is made of. So there are lots of candidates for dark matter, and this is by no means going to be an overview of all candidates of dark matter. My research has been on 2 classes, we can call them narrow classes of dark matter candidates, and asking some phenomenological questions. Okay? So first of all, if dark matter might be made of either a new particle or several new particles. This particle could be some new fundamental particle, but it need not be fundamental. It could also be some composite particle. And I'll show you an example. The phenomenological question I've been asking, I'll talk about in this talk is, can it have interactions with standard particles? And in particular, may it scatter elastically with nuclei and protons? And again, I'm going to approach this not from a model building point of view, but from a purely phenomenological point of view. What consequences would this have on observables? The second dark matter candidates we're going to talk about are primordial black holes. So those would be black holes which would have been born well before the first stars would have formed, very early on in the history of the universe. And they would have been born if the universe was sufficiently clumpy on small scales. Here, the phenomenological questions I'm going to ask, again, I'm not going to model build primordial black holes, but just ask, okay, what kind of masses they may have and what kind of abundances they may have. They may not be all the dark matter. What abundances can they make? Okay, so the observables of choice, so I'm going to focus most of the talk on the cosmic microwave background. And here, this slide just to indicate that the CMB is now a very mature science, a very mature field, but it's still growing. There's still lots of instruments and telescopes which are being planned and which are going to measure the CMB to even better precision, sensitivity, etc. I will also briefly, and this will depend on how much time we have, talk about perhaps the observable of the future, which is gravitational waves. So as you know, LIGO has made now dozens of detections of black hole binaries. These are gravitational waves in the kilohertz frequencies. There are planned missions such as LISA, etc. But what you may not always all be aware is that there are currently some experiments which are trying to measure, which have taken data, pulsar timing arrays, in the nanohertz range of gravitational waves. And if time allows, I will talk about this at the end of the talk, but it's not necessarily, will be a bonus slide. So before we get into the thick of it, I just want to give my conclusions and takeaway messages. It's good practice. So first of all, the CMB still contains some unharvested information. Okay? Even though, again, it's a mature science, mature field, there's still some stuff to look for in the CMB. But to get this information requires both understanding it to exquisite precision, and also questioning every standard assumption that we make, and looking and considering other aspects of the data that we usually consider. And lastly, again, if we have a little bit of time, I'll talk about gravitational waves. And as a theorist, I think it's a good time to start thinking about gravitational waves because it's a new era in astronomy that has just started. Outline of this talk, I will first give you a brief introduction to the cosmic microwave background, the CMB. Then, with the freshly acquired knowledge on the CMB, I'll tell you how we can use CMB observables to test whether dark matter can elastically scatter with baryons. And here, baryons, I mean either electrons or nuclei. Third, we will talk about how we can probe primordial black holes, again, with the cosmic microwave background. Fourth, we will talk about looking for primordial black holes through their gravitational wave signature. And lastly, and this is probably going to be over time, so we'll stop the talk there, and then whoever wants to say, we can spend another 10 minutes talking about pulsar timing arrays. All right, so let's talk about the CMB. So this is a artist rendition of the cosmic timeline. This is the real artist, Carlos Bordassi, and I'm going to claim just this part here of the art. So what do we see here? So if we start the story a few minutes after the Big Bang, and the universe is then made mostly of electrons, protons, and a sprinkle of helium nuclei. All of them are ionized until about 400,000 years after the Big Bang, which corresponds to a temperature about 3,000 degrees Kelvin. At that point, the universe becomes cool enough that the first neutral atoms form, mostly neutral hydrogen atoms. Not too much happens for the first 30 to 100 million years, and then the first stars and eventually the first galaxies form, etc., up until today. So how this looks from our point of view, well, why is this recombination important? Because up until the universe becomes neutral, while it was ionized, photons could not travel a very long time. They would encounter free electrons and scatter off of the free electrons. And only once the universe is sufficiently neutral, around 400,000 years, these photons scatter for a very last time and propagate over cosmological times and cosmological distances. And we see those today. How it looks from our point of view, we are at the center of the observable universe, okay? So from our point of view, the Big Bang is a big sphere all around us. Recombination also is a big sphere all around us. Time moves towards us, and these photons I was telling you about come towards us from all directions, okay? And so this recombination era looks like a surface, again, I cannot point here, but it looks like a surface, and this is what we call the last scattering surface. These photons, as I say, were emitted when they scattered for the last time when the universe was about 3,000 degrees Kelvin. So actually they were like in the red / near infrared. As the universe expands, they reach us at much smaller energies. Typically, the universe has expanded by a factor of 1,000-fold since then. And so today they're in the microwaves. So this is just pictorially, we are at the center of this photosphere of the universe. It's very similar to seeing the sun, except that we are at the center of this photosphere. And this is what we call this cosmic microwave background. So what do you need to know about the cosmic microwave background? Its basic properties. So first of all, its frequency spectrum is consistent with being a perfect black body spectrum. Okay? essentially thermal radiation. It is as good a black body as the best black body that it was compared to, with distortions which are no more than about a few parts in 10 to the 5, about 10 minus 4 distortion. And the mean temperature, which is measured now to 10 minus 4 precision of 2.73 Kelvin, etc. The fact that the CMB is a near perfect black body, we'll get back to it briefly later on, implies that there cannot have been too much of energy injection in the early universe. Okay, so not too much energy was dumped into the photon baryon plasma in the early universe. You can set some limits on this from this observation. The second aspect of the CMB that you need to know is that this temperature of the black body is not the same everywhere. It has some small fluctuations, which are a few parts in 100,000, correspond to 100 microkelvin or so fluctuations. And moreover, the CMB is polarized with yet an order of magnitude smaller amplitude of the polarized signal. These are the latest full sky measurements of the CMB by the Planck collaboration. So one property that we will go back to again later on is the fact that these anisotropies in temperature or in polarized intensity are expected from theoretical grounds, and they're observed. Sorry?
Can I ask you something? You are saying delta T is 100 microkelvin.
Yes.
Then surely it is not a Planck black body to the accuracy of 100 microkelvin.
So
simply because it is a mixture of different.
That's true. That's true. But I think this was a quadratic order.
So somehow you, okay, when you average.
That's right. So if you average multiple black bodies, you get, actually, it looks like a Compton-wide distortion, but it's only a quadratic order.
I see. Okay.
So then it's like 10 to minus 9.
Yeah, clear.
Okay, so an important property of these anisotropies is that this is a random Gaussian field. And it's moreover statistically isotropic. What this means is that, in these maps you have of order million pixels. I don't know the exact number, but of order of a million pixels. And you can compress these maps into their angular power spectra, which is the variance of temperature or polarized temperature as a function of multiple, as a function of Fourier mode, or rather harmonic mode on the sky. And the CL that I'm going to be showing you next, the CLs are these angular power spectra. Okay, so these CLs, this is what they look like. Again, this is the variance of temperature fluctuations as a function of, this is basically an inverse angular scale, and you can also extract the polarization fluctuation and the temperature cross polarization fluctuation. This is the data, and this is the best fit theoretical cosmological model we have to fit this data. This is a model which, in the end, is rather very simple. It just requires Einstein's theory of gravitation and basically Boltzmann's theory and Thomson's scatter. It's a rather simple model, and it only has 6 physical parameters, one of which is how much dark matter there is. And if you try to mess up with the abundance of dark matter, if you try to reduce the abundance of dark matter, you're going to get a terrible fit to the sun. Okay. Now you may ask, how the hell can we know so precisely that we have 84.3% of dark matter without knowing what it is? Okay, so we can do so because all we need to know to assume about dark matter is that it is some substance which is conserved, so we can write a conservation equation for it. And that is a substance that has no pressure and no interactions besides gravity. So it falls freely in gravitational potential. So as long as you have a substance that satisfies these equations, the only unknown is what is the overall abundance. Okay. All right. So yeah.
Will be out of curiosity, you're varying the amount of dark matter if the parameter is constant, or are we getting?
Yeah, all the parameters are constant. Yeah, I'm not doing that. It's not as sensitive.
Curious.
But I did ask Kimbali if she could actually do a no dark matter fit to the CMB, and it's like the Monte Carlo chains don't even converge. Okay, yeah, it's not as sophisticated as trying to get the best fit without dark matter. Okay, so I want to spend a few minutes talking about something that I've worked a lot on, and which is a very important aspect of calculating the CMB angular power spectra, which is this epoch of recombination. So the time when the universe went from being fully ionized to mostly neutral, around 400,000 years. So this is the pretty picture, and this is what we want to calculate in practice. We want to know what is the fraction, the ionized fraction as a function of time. And the reason this doesn't start at 1 is because it's defined by normalizing to the total abundance of hydrogen. And there is something like 8, there are 8 helium nuclei per 100 hydrogen atoms. Hence it starts at 1.60. So just to illustrate why this is an important part of the calculation, So these CMB anisotropies, which I'm showing you in the power spectra here, that I was showing before. What I'm going to be doing here, I'm going to add a little bump to the ionization fraction on top of the standard history. So a 10% bump, and you're going to see how this bump affects CMB temperature and polarization power spectrum. So this is a really dramatic effect because 10% is actually a really dramatic change. But so the number to keep in mind is that CMB anisotropies are sensitive to sub-percent, to around 0.1% precision. You need to have your recombination calculation accurate to about 0.1%. Okay. In order to make sure that the cosmological parameters you extract are indeed unbiased. Okay. Another thing about recombination, so the way that the data is fit by the theoretical model is not, you cannot invert the data to find the best theoretical model. The way that you do so is that you forward model in a Monte Carlo Markov chain. So you do this millions of times. Okay. So you cannot afford to have, some n-body simulation run. You need to have something that runs quickly. And so you need to have calculation which is accurate to 0.1% level and that runs very quickly so it can be run in. So I thought I had solved this problem completely during my thesis, and we wrote this code HIREC, which takes about 0.1 second per computation and is accurate, estimated to be 10⁻⁴. But HIREC was not actually used because I don't know if it's political reasons or what. But now I asked Nanu, who must be in the audience, my student Nanu, and he wrote a new version of HIREC by using smartly done correction functions. And this new version of HIREC has the same accuracy over a very broad range of cosmological parameters and runs 500 times faster. So I expect this will be the new standard code for cosmological recombination. I will not be able to discuss in detail, but I just wanted to point out that Nanu has been working on other stuff related to perturbed recombination. So you can ask him about our paper on how you can use the indirect effect on recombination to probe the initial conditions in the universe on extremely small scales, which are not directly observable. And we're currently working on asking the question, can we explain the Hubble tension in principle by perturbing recombination? Before moving on to the next part, I also want to, since one of the people here is in the audience, I don't see Abi. Abi is there, okay. So if interested, you can ask Abi about this paper on quadratic estimators for CMB weak lensing. So the 30-second version is that the CMB photons do not actually propagate on a straight line to us. They are lensed by intervening gravitational potentials. And you can use this to try and reconstruct the gravitational potential between the CMB and us. Therefore, infer properties of dark matter, neutrinos, et cetera, et cetera. So it was thought for a while that the Hu and Okamoto estimator was the absolute optimal quadratic estimator. And we showed in this paper that it's not true. And actually, one can find an even better estimator that can gain up to 11% sensitivity. And then we also mentioned this paper with Misha Ivanov, who is now at the IAS, with a very provocative title, H0 tension or T0 tension. So if you're familiar with the Hubble tension, we pointed out in this paper that the Hubble tension, that there's a degeneracy between the Hubble parameter H0 and the mean temperature of the CMB. And you could recast this Hubble tension entirely in terms of a T0 tension. But I think what is more important in this paper and what will have a longer shelf life is that we give a detailed explanation of how exactly this very basic parameter, the average temperature of the CMB, how does it enter into the calculation of CMB anisotropy power spectrum. So this was for just the advertisement. Now, before moving on to the next parts, these are the concepts again we're going to use later on. So first, as I said, the frequency spectrum of the CMB is consistent with a perfect black body. It has very tiny upper limits on deviations away from a perfect black body. And we can use this to set limits on how much energy has been injected or extracted from the early universe, from the plasma in the early universe. Secondly, that the temperature fluctuations and polarization fluctuations are expected to be and observed to be nearly Gaussian distributed. And lastly, that CMB anisotropies depend very sensitively on recombination, meaning on how exactly the universe went from being fully ionized to mostly neutral.
So can I ask you, when you say they're expected to be Gaussian, do you mean inflation or do you mean?
Right, from inflation, yes. or yeah, I guess maybe I should just say observed to be. But I'll detail a bit more. So they're observed to be if you search for specific deviations. So if once you open the box of, if you say something is Gaussian, there's one thing that you can measure is the power spectrum. If something is non-Gaussian, then there's an infinite ways that it can be non-Gaussian. So yes, I should maybe not say expected to be, but on the simplest, I guess, single field inflation, they're, I guess, expected to be mostly Gaussian. Okay, so let's now use our freshly acquired knowledge about the CMB to see how we can use this to test whether dark matter may scatter elastically with either protons or electrons. So basically, we're asking from a purely phenomenological point of view, again, not from a model building point of view, what does the CMB, what can it tell us about the magnitude of this cross section of dark matter with protons or with electrons, under the assumption that dark matter may be some particle, which is either fundamental or composite. So the sort of the king experiment to go after this are direct detection experiments, because they're literally looking for elastic scattering of dark matter with either protons or electrons. They typically do so by having large containers of noble gas in liquid or gas form. Typically, they're deep in the ground, and they have been able to set some rather strong limits on the, say, dark matter nucleon cross section as a function of dark matter mass, or dark matter electron cross section as a function of dark matter mass. Okay, and so the one thing I want to point out here is that these limits typically reach some limit. They do not go past some low enough mass. So this is about 3 GeV, 3 times the mass of the proton in this case, and about 20 MeV, so 40 times the mass of the electron in this case. Okay, so as I will try to illustrate, you can complement these direct detection experiments through cosmological probes, astrophysical probes, in particular the cosmic microwave macro. So how have people gone about to look for these signatures of dark matter baryon scattering in the CMB? So first, in CMB anisotropy.
Of course, there is no guarantee that what you see in the lab is what constitutes most of them.
Absolutely. So thank you very much. So these not only have this limit here, but you need to interpret these results. And to interpret these results, you need to know, first of all, the local phase distribution of dark matter on Earth. And yes, there are some systematics that you need to know. So it's nice to try and look for these with some cleaner tests, such as early universe tests, such as the CMB. So, for example, you can look for dark matter baryon scattering through CMB anisotropy power spectrum. The main underlying physics here is that instead of having your simple dark matter that just goes along geodesics falling into gravitational potentials, if dark matter can scatter with protons or electrons, it will feel a drag force from protons or electrons. Okay, so it will have an additional force here in the dark matter momentum equation. So the basic physics is that there's some momentum exchange resulting from this scattering, and this will affect how primordial initial perturbations evolve in time. And they will affect the CMB.
You need to consider the scattering of dark matter with dark matter.
I will talk briefly about this. Okay. So if you have just dark matter scattering, it does not affect the CMB very much, but in combination with dark matter and scattering. So this is from this paper by Gordbrook and collaborators. This is just to illustrate visually this notion that these CMB limits, and this is also Lyman alpha limits, can complement these direct detection limits by being able to probe, albeit much less sensitively, but they can probe lower masses on the left here. And also it turns out that the deep underground direct detection experiments have some ceiling, because if the dark matter scatters too much, it cannot reach the experiments, so we don't have a signal. So the CMB probes do not suffer from these issues, so they are complementary. Another way you can look for dark matter baryon scattering is through their effect on CMB spectral distortion, as we pointed out in this paper with Jens Kuba and Mark Minkowski. The basic physics is what? If dark matter can scatter with protons or electrons or photons directly, it will be able to exchange heat with the photon baryon plasma. In particular, it will be able to actually, it turns out, cool down the photon baryon plasma. And if you inject or extract heat, as I was saying, from the photon baryon plasma, this distorts the black body spectrum of the CMB. by not observing these distortions, you can set some limits. They're not very good limits, it turns out. But here I'm showing that you could also, if we ever build a spectral distortion experiment, and there is talk in the community about this, that would be sensitive to down to 10 to minus 9 rather than 10 minus 4 spectral distortions, you could explore parameter space, which in some cases has not been explored yet. Let me point out, because I know some of you have worked on similar aspects, that those are really purely phenomenological limits. So these are not cross sections which are part of a special, I know Kara, you have recently a paper, they're not part of any specific model of dark matter. So if you actually take a specific model of dark matter, there can be other limits that can be added to this. So the common point of these CMB limits to dark matter baryon scattering is that all of these probes, and I've only mentioned the CMB ones, but there are also probes relying on the alpha forest and galaxy satellites and things like this. All of them rely on the very simple fact that if you have scattering between dark matter and baryons, this induces a drag force between them, momentum exchange, and this induces the exchange of heat between them. So from the baryons point of view, baryons fall under gravitational potentials, they have a pressure, and we add a drag force. They have a temperature which, once they decouple from the photons, evolves adiabatically, and they're going to have some heat injected or extracted from due to scattering the dark matter. The standard approach in all of the work section before, and really this is all across the board, is to assume that dark matter has a Maxwell-Boltzmann distribution of velocity. Why? Because this tremendously simplifies the calculation. So then this drag force here is just going to be some rate times the relative velocity of baryons in dark matter. This heat exchange rate is just going to be some other rates times the difference of temperatures. And these rates are going to be proportional to the number density of dark matter times the velocity average cross-section. These equations can then be complemented by the ones for dark matter velocity and temperature obtained from conservation of momentum and conservation of energy. So basically, if you make this approximation, you see that you have a set of ordinary differential equations. Those are solved anyway. And so all you do here is that you add some additional term to perturb these equations. Now, why would dark matter have a Maxwell-Boltzmann distribution of photons? How can this happen? Either it will have a Maxwell-Boltzmann distribution if it's in close thermal contact with the thermal bath, which is with, for example, baryons, which are thermal. But it turns out that all the CMB probes depend on scattering after dark matter has decoupled from baryons. So the way to maintain this distribution is if dark matter can self-scatter efficiently. Okay, just we know this since Boltzmann. If dark matter can self-scatter efficiently, in particular, if it keeps self-scattering well after it has decoupled from baryons, then it will maintain a Maxwell-Boltzmann distribution.
But isn't it actually not so far from Maxwell-Boltzmann, like when they do computer simulation?
Which simulations? Which simulations of?
Oh no, I mean without any of your scattering process,
Yeah.
It's just conventional dark matter. Of course, it is not precisely Maxwell-Boltzmann, but isn't it pretty close?
But you're talking about
like today.
So I'm not talking about today. Here I'm talking about early universe. I'm talking about early universe. So in the without scattering, it would be just
Like a
perfectly
conventional,
cold.
what will it be in conventional?
Conventional without scattering, it would be perfectly cold. It would be Dirac delta. Zero velocity, zero temperature, right? So I'm not talking about the dark matter distribution close to Earth, which is sort of, but actually not order one, probably not Maxwell-Boltzmann. Here I'm talking about at high redshifts, the
When it should
distribution
have been exactly zero.
without dark matter baryon scattering, it would be zero temperature. But when you add dark matter baryon scattering, it gets heated up, but it doesn't need to be heated up.
Yeah, clear.
So I'll go back to why I think it's important. So
Yacine,
yes,
sorry,
yes.
that if you're interested in, if your only motivation is to looking at how the CMB is modified by the interaction, then you don't care about whether the dark matter stays in thermal equilibrium, keeps the thermal distribution after it's decoupled, do you?
Well, as we will see, it does affect. So this assumption actually does affect So give me 2 minutes and I'll explain why I think it
Okay.
matters.
Maybe you're interested in the transition as it's falling out of coupling or something. Okay.
So I'm
thanks.
interested in getting, so I'm interested in using the full power of, sub-percent level CMB measurements. And we will see that this assumption can lead to order 2 factors of 2 differences. And
Okay.
as I will argue also, if you built in the assumption that your dark matter self cross-section basically is large, then you make yourself blind to this parameter. But if you do, open the box and say, okay, if you build some formalism which allows you to also include this parameter, then in principle, you should be able to probe simultaneously the cross-section with baryons and with dark matter.
Okay, great.
So that's my motivation here.
But isn't it enough for it to be thermal some early enough epoch? And then typically it decouples, well, the thermal distribution redshifts, but it remains thermal, right? So,
but it doesn't decouple instantaneously.
Right, but it's a small correction. So that's
it's only true. It's factor 2. Yeah.
It won't be really a delta function for standard dark matter, even if it doesn't interact at late times, right? It will be some small correction.
It's not small. It can be factor 2. That's what I'm saying. It's not small.
He's saying that suppose it was called collisions will distort it and will produce something.
Well, collisions will make it actually exactly thermal up until the time when collisions stop being relevant. Collisions with baryons. It's the detailed exchange of momentum and heat, even after dark matter decouples from baryons, matters for CMB probes. And so, yes, if you're interested in like, order 1 limits, this is fine. But again, like we have this beautiful percent level measurements. If it's, we do a little bit of hard work in theory, and we should be able to get more information. That's my field here.
So when you say a factor of 2, you mean something like the average over temperatures that range over a factor of 2?
The heat exchange rate, for example, which is the quantity that directly affects, say, spectral distortions. I think the momentum exchange rate also should be. I'll show this like really next slide. Sorry.
But the point is that it's affecting it through the way that affects the growth of structure in dark matter, I guess.
It will,
But anyway, we'll wait.
I'll show you exactly what I mean. But let me show you one slide from your paper, Glenn, first to make my point also. So the fact this is not a guaranteed property of dark matter, and the good thing is I didn't have to look too far because in Glynis's sexoquark model, where dark matter would be a composite particle made of up, down, and strange quarks and antiquarks. This is from a courtesy of Xinsheng Su. I don't know if you're in the room or not. Yes, thank you. So here what you can see is that in blue you have the dark matter cross-section with protons as a function of some coupling parameter of the sexoquark with nuclei. And here in orange, and I put in thick line the most likely value of this parameter, you have the dark matter self cross-section. And in this model, the dark matter has a mass which is about twice times the proton. Therefore, the abundance of dark matter is about 3 times that of nuclei. So the point is that this is, if you take this line, it is systematically lower than the blue lines. So this is a model where this is broken completely. It's actually the other way around. So in this model, dark matter self-interacts much less than it would interact with baryons, typically. But also there's this uncertainty, okay? So it could actually interact more. So the point I wanted to make is why this matters is that, first of all, you could get these order 1 errors, as I'm going to explain. And if you have spent all these hundreds of millions of dollars for 0.1% precision measurement, we can sweat a little bit as theorists to get better than order 1 errors. If you have order 1 errors, if you have some sliver of parameter space which remains, okay, this does matter. But I think even more importantly, again, if you have built in your formalism that some parameter is large, then it means you cannot search for this parameter. Okay, so if you want to just purely phenomenologically search for simultaneously for dark matter proton and dark matter self interactions, one needs to go beyond this Maxwell-Boltzmann approximation. So why is this something that's difficult? Because instead of having, for example, the heat exchange rate, which is just some overall rate times the difference of temperature, this now becomes some integral over the velocity distribution of dark matter. Instead of having the temperature of dark matter just evolving according to an ordinary differential equation, we have to solve for the Boltzmann equation for the dark matter velocity distribution, where these collision operators account for scattering with protons or with itself. And these collision operators are integral operators. So instead of having a simple set of ordinary differential equations, we have integral differential equations. This is, even though actually nobody ever pointed why they would do this Maxwell-Boltzmann approximation, but this is, if you do anything else, this is what you have to deal with. So what I did as a first shot is replace this by a partial differential equation by approximating the collision operator of dark matter baryons by a Fokker-Planck operator. So this is a diffusion operator. And what I show here, so this is now hopefully answering a little bit of the questions. So first of all, the velocity distribution in some cases can differ by order unity from Maxwell-Boltzmann. And what is more relevant here as a function of time, basically, the fractional change in heat exchange rates can reach 150%. Okay, so my point here is that you can get a heat exchange rate, which is something that directly affects observables, which can be off by factors of 2. So your limit can be off by a factor of 2. As long as it's just limits, it's fine. Take them to factor of 2. But if we are a little bit optimistic, because we can't just hope to just set limits forever. Okay, we're building this maybe in the case that someday one searches the data and finds infection. Then if you detect something, it would be good to be able to also explore self-interaction simultaneously.
Sorry, what are the different points of the different stuff?
This is just as a function of time, and the plot, the blue dots here correspond to these colors. So this is an evolution of the distortion of the dark matter velocity distribution in time. Now, if you have ever thought about the Fokker-Planck approximation, you know it's a diffusion approximation, so it only works if, in this case, if scattering is diffusive, meaning if dark matter changes its velocity by small amounts. But if you think of a small, light dark matter particle, imagine a ping pong ball, and much lighter than protons, imagine a billiard ball, the dark matter will change its velocity non-perturbatively. So this whole thing might be a very nice looking sophistication, but actually might be just as wrong as the Maxwell-Boltzmann approximation. And so Sarur, who is right here, actually solved the exact integral differential equation in a simple setting, which is neglecting spatial perturbations. And she checked effectively that she checked that the Fokker-Planck approximation, despite even in the cases where it's non-diffusive, gives you results which are reasonably accurate. And why this is interesting because it means that we can now use the simpler partial differential equation rather than the full integral differential equation, and we can implement this into the CMB-Boltzmann codes with the hope to maybe be able to again simultaneously test for dark matter proton and dark matter self-interaction. Okay, the last part on this dark matter baryon scattering. So the next project of Sarur's is going to be actually maybe much more complicated. So I want to
For the experiment, there should be Z dependence, but in theory, it should be very weak.
People on Zoom, you have to mute
Can you
yourself.
mute yourself, please?
Okay, so I told you that CMB was Gaussian. Where does this come from? If we start with some Gaussian distributed initial conditions, and then everything evolves linearly, and we know the things in the standard picture evolve, the linear approximation is very accurate, then the end result, CMB and isotropies, are also Gaussian distributed. So this means that the way that, for example, one searches for dark matter baryon scattering signatures in CMB power spectra is by looking for small changes. So I have a standard CMB power spectrum, so the variance of temperature, and I'm looking for some small change, which has to be, larger than a few tenths of percent. And this is how I can look for dark matter baryon scattering. Okay. Now, if something implies nonlinearity in the evolution, you will get, even if you have Gaussian initial conditions, you will get some non-Gaussian CMB anisotropies. And as it turns out, dark matter baryon scattering does lead to some nonlinearity. Even if we look at the Maxwell-Boltzmann approximation, which would be correct in the large limit of large self cross-section, this term here and the momentum exchange rates, so this rate here, actually is some function of relative velocity. So the point here is that this additional term is a fully nonlinear term. And so this means that we expect some non-gaseosity. This means that instead of just looking at changes in the standard power spectrum, we will have some qualitatively new statistics, some statistics of the CMB, which normally vanishes in the standard picture, the 4-point connected 4-point function, but in the presence of the scattering should become non-zero. Okay? So I think this is interesting because instead of looking for a small change to something that's non-zero, we can look for something that usually is zero and then look for some new signal. Okay, are there any questions on this before I start the second third of my talk? Yeah.
The dark matter scattering is variance and its interactions with anything besides gravitational interactions.
No, those are like actual, imagine the dark matter is charged, say. Those are non-gravitational interactions, they're actual interactions.
Are those any interactions that we know are standard model interactions? Are those interactions that you're familiar with?
No, so again, here I'm not, so some people here work on model building, theoretical models for dark matter. If dark matter is some new particle, maybe it has absolutely, it doesn't talk at all to the standard model, that's possible, but maybe it has some way of talking to the standard model. Maybe there's some very weak but non-zero interactions, non-gravitational interactions with the standard model. And so here I'm not looking for general interactions, but specifically, okay, could it scatter? Okay, let's talk about primordial black holes. Yes.
How do you know that they're on scatter with dark matter?
Well, I don't know, so that's what I'm asking. Say, I don't know, but maybe I just asked the question, can it scatter with baryons? Let's predict what kind of consequences this would have on the CMB.
Also, why specifically?
By baryons, I mean nuclei, electrons. You can also look for scattering with photons.
Surely not electrons. You don't mean electrons by baryons.
No, here I do. Here I do.
I thought you had separate cross sections for electrons and baryons.
Yes, we have separate questions. But I call them baryons
Actually,
together.
the bonds are different.
The bonds are different, yes. Okay,
That's true.
let's move to primordial black holes. Okay, so primordial black holes, as I briefly explained, so I did not explain at all actually, but they're in principle as good a candidate for dark matter as a particle. Why? If you think of the universe on very large scales, the universe doesn't really care if dark matter is made of things as light as electrons or things as light as heavy as the sun. Okay, so it's dark matter could be something that's very heavy, very light. It's difficult to pinpoint unless it has interactions beyond gravitation. Okay, so besides being a dark matter candidate, primordial black holes also give some indirect window into the unknown conditions of the universe on very small scales. Why? So this is pictorially the RMS initial fluctuation, say the density or curvature of the universe as a function of length scale. We have very precise measurements from the CMB and from large scale structure of the initial conditions. We can infer the initial conditions on length scales of millions to billions of light years, megaparsec to gigaparsec. We have some upper limits on 0.1 kiloparsec to megaparsec length scales from the non-observational spectral distortions. As it turns out, if you had some perturbations, they would dissipate and they would inject into the plasma. But at smaller scales, we have very little information. There could be some interesting and crazy physics hiding there. In particular, if you have very large, sufficiently large initial perturbations, they could, in principle, form primordial black holes. So not observing these black holes either tells you, okay, they're not a dark matter, but can also tell you something about, even if it's just a limit, about the amplitude of small scale fluctuations that we cannot, again, probe directly. This is to show you the status as of 2021 of the limits on the fraction of dark matter in primordial black holes. So this FPBH is no more than 1, okay, is the fraction of dark matter made of primordial black holes as a function of primordial black hole mass. So if you look at this plot, you can see that primordial black holes are essentially ruled out as a dark matter everywhere except in this 3-4 order of magnitude window. So except if they are basically of roughly asteroid-like masses. Okay, and so some very cheeky people have come up with ways to say, well, dark matter could be all primordial black holes. It turns out that primordial black holes are not going to have some Dirac delta distribution, but should have some broad mass distribution. And here, for example, you could, this is an example of a mass distribution calculated by people where all the dark matter would be primordial black holes, okay, mostly of asteroid masses, but you would have some tail in the high region here. So I will actually be focusing on this region here, on high solar masses and above primordial black holes. And I think it's interesting, one, because you could potentially probe the tails of some extended mass distribution. And two, again, because even if primordial black holes are not all of the dark matter, again, they give you some information about initial conditions. So this is the range I will be focusing on. This range, the limits are dominated by CMB anisotropy limits. Those are limits that I worked on with Mark and Minkowski. And there also can be potential limits from Langkov, which I may or may not get to talk about.
So this will be like a micron, right?
Micron.
Like the size of this thing. Just to understand why in microdays it doesn't.
They're not micron like the refractory
Yeah, yeah,
radius. I mean, this here is solar. Oh, you mean like here?
Yeah.
Yeah, they would be tiny. I don't know if it's microns, but yeah, maybe it's even less than that.
Just to understand why microdays in that.
Yeah. Yeah, I'm not sure exactly why it stops here. So let me tell you briefly about the underlying physics for how come the CMB can set some limits on primordial black holes. So if you have a bunch of black holes in the early universe, so again, the idea is that they would be formed even before the first stars were born, very fractions of a second after the Big Bang, they would necessarily accrete some gas with some accretion rates m dots. First need to calculate. This accretion would power some luminosity. At minimum, the gas as it falls into the black hole would get compressed, heated up, ionized, and would emit free luminosity. So there would be some luminosity which is proportional to m dot c squared with some efficiency parameter, again, to estimate. So this means that these black holes would inject energy into the early universe with a rate per unit volume, which is proportional to the fraction of primordial black holes times their individual luminosity. This energy is injected close to the black hole. Imagine you have these black holes radiating gamma ray photons, but these photons don't necessarily interact with the rest of the gas right away. So it takes some time before they actually deposit their energy into the plasma. So what we're more interested in is when, as a function of time, this energy is deposited, and typically this is related to the energy injection by some time-dependent Green's function. Part of this energy which is deposited into the plasma is in the form of additional ionizations. So the rate of change of the free electron fraction will be modified by something which is proportional to the rate of energy deposited into the plasma. Yes, let me finish just this and then I'll get your question. And once you modify the rate of ionization, you're going to modify the recombination history, which, as I said in the beginning of the talk, has can affect quite strongly the CMB angular power spectrum. So if you manage to calculate all this, you should be able to figure out what is the effect of primordial black holes on the CMB power spectrum. Yes?
To compute the accretion rate, you have to make assumptions about or it's just one the accretion.
Here was just one accretion. Yeah, you didn't make any assumption about that.
And for the epsilon,
no, here I didn't take 0.1. I actually tried to calculate this from first principles, assuming free radiation. Yeah, but this is a part. So just to show you, so when you go through this procedure and you analyze Planck data, CMB anisotropy data, you can set these limits by not observing any effect. But here is just to show you, like I took two. So you have to model how the accretion flow gets ionized and what its temperature to estimate the free radiation. And just by making two extreme assumptions about how it gets ionized, you get 2 orders of magnitude difference. So this is hugely uncertain as the accretion physics, and something that would be great to revisit. So if you're an expert, come talk to me. But what I want to show you now is that if you, in addition to these uncertainties, I mean, regardless of these uncertainties in accretion physics, what Trey and I have been working on is some qualitatively different signature on the CMB, which is again non-Gaussian. So how does this work? So far we only accounted the CMB power spectra limits only account for the spatially averaged effect of primordial black holes. Now, primordial black holes, so again, if you take the Bondi rate, as you were just saying, as a simple approximation for the accretion rate, the local accretion rate depends on the local velocity of the gas that's accreted. So if the gas is moving really fast compared to the sound speed versus if the gas is kind of sitting still, you're going to have a very different accretion rate. And as a consequence, you're going to have a very different luminosity. So pictorially, this is how it looks like. We actually know, and this is independent of what makes dark matter, because on very large scales, it doesn't matter what dark matter is made of, but we can calculate from linear theory what is the characteristic relative velocity between the gas, baryons, and dark matter, in this case, primordial black holes. And it so turns out that this relative velocity is typically supersonic with a Mach number of 5. This means that this term here is typically larger than that term here. If you plug in this luminosity here, you see that the actual luminosity of primordial black holes is a very wildly varying function of space. And to get you some understanding here, each one of these blobs, there are millions and millions of primordial black holes. Okay, so those are on scales which are much larger than the individual separation of primordial black holes. So it doesn't really matter again what dark matter is made of, as long as we have some idea of how much it weighs. So this means that the energy injection is inhomogeneous. It depends on not only time, but also on spatial location. This means that the energy deposition and later on the effect on recombination should also be inhomogeneous, depend on space. So this is the picture I showed you before, the CMB last scattering surface. If recombination is inhomogeneous, instead of having a nice sphere for the surface of last scattering, we're going to get some crinkled up sphere. And it's well known that if you have some crinkles in the surface of last scattering, this induces non-Gaussianity in the CMB. Okay? A different kind of non-Gaussianity from the one I was talking about. Because again, there are an infinite ways for the CMB to not be Gaussian. There's only one way to be Gaussian, and there's an infinite way to not be Gaussian. So we've been starting exploring this with Trey, and I think I'll probably stop in like 5 minutes. I don't know if I'll go over the language parts. So what the first question we asked the Trey Jensen over there is, so you have inhomogeneities in the way that energy is injected. Does the energy deposition remain inhomogeneous? So instead of calculating simply time-dependent Green's function from injection to deposition, what Trey did is calculate a time and space-dependent Green's function from injection to deposition by implementing radiative transfer simulations. So this is just to compare, if you're familiar with Tracy Slatter's work. She is the expert in computing these time-dependent Green's function, and this is as a check of our time-dependent Green's function. We recover her results, and in fact, for the cases we considered, energy injection from gamma ray photons, we actually think that our code is a little bit more accurate than what Tracy Slatter has done. And this is the new part of the calculation, which is the spatial aspect of this injection to deposition Green's function. The bottom line, what we found in this first work, is that due to inhomogeneous injection of energy by primordial black holes, the free electron fraction does fluctuate on scales of about 100 megaparsecs, and with a root mean square, which is comparable to the mean effect. Okay? And so this is promising for the non-Gaussian signature of the CMB. And so Trey and I are now putting the finishing touches in this paper on calculating the trispectrum, which is it's a pretty horrendous calculation. So it's a lot more complicated than just this equation might seem.
So you say your code is maybe more accurate than the Tracy's code, which is used by Planck to set balance and energy injection. So those balance.
Well, I mean, it's in the very specific case that we consider, because we only consider injection of gamma ray photons. There are some things which I think we do a little bit more.
So like for dark matter annihilating gamma rays, like
Yeah,
Like the
but it's
bounce
like
rate makes
tiny, yeah, well, I don't think it's like, I don't think it's gonna change the bounce rate by very much. I'm not talking about factor. Okay,
And why is it trispectrum and bispectrum?
good, because since the luminosity depends on the relative velocity squared, the Fourier transform fraction is going to be essentially quadratic in the initial curvature perturbation, as opposed to just linear, and the lowest order signal is a trispectrum. Same thing for dark matter and scatter. Okay, so I can do two things now. We can either stop here, or we can either go into this section, or we can go into the PTA section. So choose your own, choose your own route. It's going to be.
I think we can finish in about 5 minutes.
5 minutes.
That's enough time for either of those.
Okay, you know, I'll just do the last section then on the nanohertz background. It's just going to be a little bit of a different thing. I have to show you a movie that's cool. This is no context here, but it's a cool movie, so I'll show you the movie. This is work by Derek Heyman, who was supposed to talk here, and so you can ask me later why we did this, but we asked the question, how are primordial black holes spatially distributed as a function of time? Those are n-body simulations on very small boxes, 30 kiloparsecs. Typically, n-body simulations are around like gigaparsec boxes. And each one of those points is actually of the mass of a primordial black hole. So they're really resolving primordial black holes. And just to show you, you start from, on small enough scales, primordial black holes are randomly distributed. Therefore, there are some Poisson fluctuations in their density. And therefore, they're going to form structure in the universe much earlier than if you had regular dark matter. And this is how it looks like. So at redshift 99, 17 million years after the Big Bang, if you had no primordial black holes, the universe would still look rather smooth. But if dark matter is made of, say, 10% of primordial black holes, actually there are already structures in the early universe.
Why is that? I
Because you have
thought the
Poisson
mass of the
fluctuations.
dark matter particle was, oh, Poisson.
Poisson fluctuations, those are
We
really
just
small
have
scale.
Poisson.
Yeah,
How many of them stay single and how many go to binaries?
good. So maybe I'll just talk about this section then. Okay. Okay, so this part on using LIGO for. Okay, so what LIGO did, LIGO has observed dozens of binary black holes. The range here of masses, from a few to tens of solar masses. So you can use this, of course, to try and constrain primordial black hole. If you have a model for the mass distribution of primordial black holes versus astrophysical black holes, the spin, etc., people have been looking into this, comparing the mass distribution, the spin distribution. But there's a 0th order quantity, which is just the merger rate. Okay, LIGO can estimate a rate of binary mergers per unit time, per unit volume, from what is observed, and a very 0th order test of primordial black holes. Do they or not saturate, or are they way below, or would they go above this rate if they made all of the dark matter? So how do you form primordial black hole binaries? There are 2 channels. So there is a channel in the late universe. So in today's galaxy cores, and in fact, dwarf galaxy cores, which are very dense, primordial black holes are just zooming around, and there's some small chance that if they pass close enough to one another, they're going to radiate enough gravitational waves to form a binary. This is very much like radiative recombination, the first part of the talk, electrons and protons forming hydrogen atoms. Same thing, except it's a gravitational wave recombination. Okay? So in this paper led by Simeon Bird, when we were at Hopkins, we estimated this rate. We found that if dark matter was entirely made of primordial black holes, these would produce a merger rate, which is comparable, a little bit below, but comparable to LIGO merger rates. And hence, we ask this question, did LIGO detect dark matter? This paper has a, yeah.
So this assumes that the initial distribution is Poisson.
This did not actually account for Poisson, and I corrected it later. It doesn't change things by much, even though every subpiece is changed by like orders of magnitude. The end result is not.
Okay. And I mean,
interestingly enough,
is there a good reason to assume that it's Poisson or not Poisson? I mean, if you don't know how to generate it in the first place.
I think because when they are generated, it is the entire horizon volume that collapses into a primordial black hole. So for them to have some amount of clustering would require regions which are separated by multiple cosmological horizons to somehow have correlations. So I think if there's some non-Gaussianity that would work, but in general, I don't think that would be the case.
You didn't have collapse on sub-horizon scales.
At least the center picture is that it's the entire horizon volume, or like a good fraction of it that collapses into a black hole. So yeah, so the horizon of the black hole is actually the horizon of the universe at the time of collapse.
But didn't you tell us that at solar mass, only a tiny fraction can be in the form of black holes?
Yeah, that's true. With this paper, we completely ignored all the limits. In this paper, we completely ignored all the limits, and still it has 1,000 citations. So, you know. It's not my favorite paper now. So another way to form binaries, which actually turns out to be much, much more efficient, is in the early universe. And this was actually known well before our paper, and again, we weren't aware.
Well, you just forgot about this.
No, we just didn't know. So the idea there is what? If you assume that black holes are Poisson distributed on small scales, then there's some chance, if you take one black hole, there's some chance that it has a very close neighbor, just as a pure chance, okay? And now imagine this is all in an expanded universe, but if you have 2 point masses which are close to one another, they are going to feel each other's attraction and stop expanding and just form a binary. Just out of chance proximity. Now, if nothing happens, so this happens typically before recombination, that they would form a binary before recombination. That's why I call it the early universe channel. If nothing happens, you can calculate everything, calculate the typical eccentricity, setting major axes, you can calculate when they merge, and you can find that the merger rate would be much larger than the rate observed by LIGO if they make all the dark matter. But a lot of stuff happens in the universe between recombination and today, okay? And so you have a lot of structures that form, and so these black hole binaries then become members of much bigger nonlinear structures. They can interact with other bodies, etc., which could disrupt them. So in this paper with Eli Kovets and Mark Minkowski, and I'm not doing it justice here, what we spent most of the paper on is to make some simple analytic estimates to figure out whether, basically to figure out the effect of that stuff here. Okay, so whether these binaries forming before recombination would be significantly circularized, which would change their time of merger, and therefore whether this would drop the merger rate. And we found, based on analytic estimates, that it's not the case. Therefore, what we found is that LIGO should be able to, in fact, set very strong limits on primordial black hole binaries. So we turned the thing on its head. I didn't give it this title because the first paper were my colleagues in France, but really the title should be, does LIGO rule out primordial black hole dark matter? But to confirm this, and I put these potential limits, we need to really, we made some rather drastic analytic approximations to confirm this. And so this is why I was showing you these simulations. For example, we need to understand how the first structures form in the early universe, and we need to understand how third body encounters can affect primordial black hole binaries. I made some very simple estimates in the paper, but I think I may have overlooked some qualitative effects that can only be captured with full three-body calculations. So the bottom line is that LIGO could, in fact, set the strongest limits on primordial black holes in the 1-2000 solar mass range. But to really confirm this, we need to revisit a few pieces numerically before concluding this. Okay, I'm going to stop here now, and then if people want to talk about pulsar sampling arrays, I can talk about this. So I'll give you my takeaway messages. The conclusions again, the CMB still contains some unharvested information. You just have to know how to look, where to look. You have to, lift every little curtain.
Shouldn't it be the CMB maybe still contains, right? Because it depends on whether or not it is unconventional, right? If it is fully conventional, then there is no more information.
It contains information. If you have never looked at a specific 4-point function because we haven't calculated it yet. But once we calculate it, we can look for it. If you don't find anything, you have information, you can set the limits.
Or you can exhaust all the possible templates for non-Gaussian.
Well, you can predict some templates from physical grounds. But so if you look for a template that so far nobody has looked for, from dark matter baryon scattering, from primordial black hole accretion, and if you find nothing,
but in the
you still
boring
accept
scenario, all these searches will yield 0.
of course, yeah. But 0 is still information in the non-boring scenario. So it's a constraint. Yeah, and I will stop here. With a weird wall.
If I understood correctly, you mentioned that if we look at the results from LIGO so far, then it includes the primordial black holes. It's a combination of primordial black holes. If I understand correctly, in this picture, for instance, you only look at black holes, primordial black holes that are heavier than the solar mass. What about the possibility of having a large population of small black holes that LIGO will not be able to detect?
Yeah, absolutely. So this is what I was showing earlier on here. So you can, this, for example, is not detectable by LIGO. But so one of my motivations is so this curve here is actually, they put it in solid in this paper, but it actually is LIGO potential limits. So those I don't think will go much lower. But if we find something that's much more sensitive than the CMB power spectrum, like the CMB tri-spectrum, you could in principle say, probe this bump here. So by the way, this bump comes from what? It comes from, if you assume a flat primordial power spectrum, enhanced power, but you will have, at the QCD phase transition, you will have lower sound speeds, and this turns out to be around the solar mass or so. So this will enhance the formation of primordial black holes around the solar mass. So you will always have a little bump here. It's much lower than the limits, but if we can find some more sensitive way to probe primordial black holes in this mass range, we could indirectly probe, broad distribution.
Assuming Riota knows what we kill.
Assuming so, yeah.
Without the nanohertz?
So the nanohertz, I think they show. So I think the same authors showed that the small scale. So if you have some amplified power spectrum, primordial power spectrum, that gives you this series mass primordial black holes, I believe this would lead at second order to gravitational waves in the nanometer. I think it should be something.
So maybe one more question, if there is one. Okay. Yeah.
Do you really think there are primordial black holes as a friend?
Oh, okay. Thank you for the question. To be clear, I don't think there are. I'm not in love with primordial black holes. Neither do I hate them. I think one should look at these questions from a very distant point of view. I'm very curious about it. I think it's a curiosity. And what got me interested also is that before this 2016 LIGO stuff, because nobody really believed in all these limits were kind of loosely, not very well done. So what I've done is revisit these limits in a more rigorous way.
Yeah, I asked a stupid question.
Yeah.
It doesn't matter what we believe. Right?
I don't believe exactly. This is exactly my point.
We should be more modern.
It doesn't matter.
So there's one question on Zoom, and then we'll finish.
Oh, you are muted, David.
For once, I'm muted. So I want to build on Andre's question. I mean, if there are a lot of asteroid mass primordial black holes, how much is a lot? Like, how long would it take for the Earth to encounter something like that, and what would be the effect of that? I mean, is the Earth in some sense a detector for asteroid scale primordial black holes?
Yeah, no, this is a very good question. I have, and I would encourage you to quantify it. I don't know the answer to this question, but I think it is still, you would have very, very few, the local density of black holes is still very, very small. And I think the probability of encountering not only the Earth, but even like the Oort cloud, for example. I think some people have looked into this. You could potentially have some black hole that passes close enough to the solar system that it would disrupt the Oort cloud and then, launch some comet or whatever from the Oort cloud. I don't think the interaction with the Earth itself is something to worry about, but it could have some effects on the solar system. But I think it's still very weak, very infrequent.
And would that be consistent with the limits that are shown here?
So again, I think my understanding is that none of these would actually set limits in this range. But I can look in more detail and get back to you. Those are presumably the limits that were the most up to date last year, but I haven't looked if someone has come up with a better thing. I'm pretty sure that direct encounters with Earth would be extremely infrequent. But again, there's this question of interaction with Oort cloud asteroids.
So perhaps this is the most interesting thing, right? Nobody has invented a way to rule out this window.
Well, no, so people had invented ways to rule out this window, but they were incorrect. It was because again, it was before. I didn't look at this myself, but Craterata, as it turns out, and the students looked at this. So there were, for example, some limit based on you would explode white dwarfs or neutron stars. But remember, if you had enough, primordial black holes of asteroid mass could be gravitationally captured by white dwarfs and then heat up the core, eventually make them explode or whatever. But those are the limits that were thought about so far, and then they were shown to be actually incorrect.
Those are the window of microlensing.
Yes, there was something with microlensing. But yeah, if you think of something there, this is how you can probe.
This is a noble thing to close this window.
Yes, yeah, exactly.
So unless it's been hit by an asteroid mass primordial black hole, there's some food somewhere. So why don't we continue this over food and break. So
Okay,
thanks again.
thank you.